Emostel.
Hello everyone, you're welcome to this video. And in this video, talking about set theory, we are going to be discussing the various types of sets that we have. All right, okay, and then please mind you, if you are watching this video for the first time or you didn't start with this series, it's a continuation of a set of videos from where we started. This is like the fourth video in that series. All right, so we continue. Talking about the types of sets, there are about 12 of them. Each of them will be discussed in this video, and I want you to pay full attention to that because we'll keep learning. Even it may look insignificant as a topic, but then some things you will learn, there are some important things you'll learn in the line of this topic, and then which you will find very interesting and very useful. Let's go. Now, finite set is the first type of set we are going to be addressing. All right. A finite set is just a set that has a fixed number of members, a fixed number of elements. Okay. And I told you before, it does not matter the order of arrangement of those elements, but what really matters is the fact that there are elements there, and the elements can be counted, or there is a fixed number of elements, even though the elements may be so large in number, but the point is we still have a number. An example of such, the set of noun students, for instance, it does not matter the number of, how large the number is. Could be over 500,000 in a given semester, over 500 registered noun students in a given semester, but the fact still remains that it is countable, it is definite, it is not infinite. Do you understand? So it could be a short amount of, it could be a set that has only a few number of elements, and it could also be a set that has a large number of elements, but what matters is that it is countable, it is definite, okay? So when we have a set of such, that kind of set is called a finite set. Maybe you may wish to call it finite set. I don't know, but the spelling is just correct. Okay, so now we move on to the next one, which is the non-finite set. All right, the non-finite set is a set that may either have a starting point but doesn't have an ending point, or it has a place it ends but it does not have a place it started from, or it neither have a starting point nor an ending point. In as much as there is a condition whereby you cannot even finish counting the elements that are there, then that is a non-finite element. It represents a continuous, a set that has continuous number of elements. Like it is not definite, it is infinite. So when you have such kind of set, we call it infinite set or a non-finite set. Well, we have a few examples of such for reference. The first example that I can refer to now, if you have this, let's say A is a set of X such that, in the first video, I used two dots like a colon for such that. Yes, this one too is also valid for such that, okay? It only depends on what is used in textbook that you're using, okay? So A is a set of X such that X is an element of, like X is natural. Yeah. Okay. A is a set of X such that X is natural. Remember, natural number is a set of numbers that are positive whole numbers, like a set of positive whole numbers. That is what we call natural numbers. Okay. Now, positive whole numbers. What are whole numbers? Numbers that don't carry decimal. Positive in the sense that they are not negative. Okay, and mind you, 0 is neither negative nor positive. So when you are listing the elements of natural numbers, you're most likely not going to need to include 0. You start from 1. Do you get it now? So what are the positive whole numbers that we have? Starting from 1, we have 1, 2, 3, 4, 5. Numbers that are used in counting. Okay, they are called natural numbers. We are still going to a topic that actually talks about it much more. Okay, so this is an example of an infinite set, because if you want to represent it in a tabular form, you would say 1, 2, 3. We only know where natural number starts from. We don't know where it ends. We don't know the last natural number because the number continues on and on and on forever. Nobody knows the last number. Neither does anyone knows the first number. So we only have the negative infinity and the positive infinity. So this set extends on and on to positive infinity. Okay? And so this is an example of a non-finite set because, yes, although it has a starting point, but it does not end anywhere. Now, we have a second example. If we say B is a set of Y such that Y is an integer, Z is used to represent a set of integers, all right? Z is used to represent a set of integers. And then you have, and then maybe you say Y, capital Z for that matter. Y is negative. Okay, good. So if you want to represent a set of integers, and then you only need the negative ones among them, well, this is also another example of a non-finite set because you're going to be having something like, okay, B is equal to, I don't know the last, nobody knows the last number, the smallest number in the world. We don't know where negative number starts from. So you can say negative infinity, okay, and then you have comma until the last negative whole number that we have, which is -1. Okay, so in this case now, we did not start from anywhere, but we ended somewhere. Okay, maybe you have this, and then you have, let's just say -3, -2, and -1. No problem. Just to let you know, we have a few of them. Okay, so at the end of the day, we have the negative infinity. It started from somewhere. We don't know where it started from. And it goes on and ends at -1 because that's the last negative whole number that we have. Okay, so at the end of the day, you see that this one does not start from anywhere, but it ends somewhere. It's also another example of a non-finite set because the members of it cannot be counted. The number of members cannot be counted. Okay, so that's that. Then what if we have a third scenario that say C is a set of Z such that Z is a real number? See, the local thing in Nigeria, you say Z, you understand? So C is a set of Z such that Z is a real number. Okay, so now if we have Z as a real number, it means real numbers are all these numbers. Any number, the number you use in performing basic numeric operations, that are everyday regular numeric operations. They could be negative, they could be positive, they could be whole number, they could be fractional, okay, decimal or whatever, but they are numbers that we can work with, okay, we can deal with in our everyday life. So those numbers are called real numbers, okay? And this is a symbol for representing real numbers. However, if you want to represent this in a tabular form, you say C is a set of, we don't know where it started from, don't know, and then it continues on and on and on, okay? It might have -3, -2, sorry. In fact, we don't know where it started from, because if I say -3, -2, it means I am ignoring the net decimal, and decimal is part of it too. So it continues on and on, onto positive infinity. So it started from negative infinity, ends at positive infinity. So this kind of number, this kind of set is also a non-finite set. In this case now, it neither has a starting point nor an end point. You get that now? So that is that as per that. Now we move on to the next example. The next type of set that we have on the list here is the set of, it's called the unity set. Well, it is very possible that a set has only one element. Okay, very, very possible that a set has only one element. And if we have a case whereby a set has only one element, that kind of set is called a singleton set or a unity set. Okay, example, well, you can have, let's say, D is a set of L, okay, such that L is a month with 28 days. Well, I'm just like looking for, sometimes it's 29, but like leap year, but let's just assume it's not a leap year, okay? So we have D is a set of L such that L is a month in 28 days. Out of all the months in a year, it is only one of them that has the possibility of having 28 days, and which is the month of February. So in that case, now if I want to represent this in a tabular form, I will say D is February. Only one element present, okay? Although it is still a set. I believe you understand that. So that is how it goes. So when you have a set of a set that contains only one element, is called the unity set, otherwise called singleton set. That is that. Number 4. The next one we are talking about now is the empty set. The empty set is a set that has no elements. Nothing is inside. It can be represented as empty brackets or with this symbol, okay? Anytime we have this, it means that the set is empty. No element present. You get that? So, good. And the next one we talk about is, okay, let me just give you an example of an empty set. If you have a set E is a set of M such that M is a month with 32 days. Since it is not possible to have a month, or we don't have any months in English. I don't know about other kind of calendar, but in our general calendar, okay, there is no month that has 32 days. In that case, we will say E is an empty set because there is nothing that will occupy it. Or we just say E is null, okay? So that's how to represent empty or null sets. Okay, good. Now, okay, please, another name for the empty set is null, N-U-L-L sets. Okay, please don't forget that. All right, so we move. Number 5. We have equal sets. Well, equal sets are sets that have exactly the same elements in them. They have exactly the same elements. Okay, although the elements might be scattered, they might be scattered, but they have the same. For instance, if I say set A is equal to 2, 3, 4, and set B is equal to 4, 2, 3. Okay? Because of the fact that they have exactly the same elements, the same number of elements and the same types of elements, then we say that set A is equal to B. Okay? It means A and B are equal sets. Or you say B is equal to A, anyhow it goes. All right? So equal sets are sets that have exactly the same elements in them. It doesn't matter the position of the elements, but what matters is that the elements in them are the same. Okay? So we move. Now the next one we're talking about, which is also very important, is the subsets. Subsets. Well, subsets are sets. If you say A is a subset of B or B is a subset of A, it simply means that all the elements in B can be found in A. So you say if B is a subset of A, okay, it means all the elements in A of A can be found in B, of B can be found in A. All right. So now in this kind of case, okay, let's just consider an example. Let's consider an example. If A is equal to something like 2, 3, 4, 5, 6, 7, and then B is something like 2, 4, and 6. Okay, if A is this and B is this, it simply means that the elements, since all elements of B can be found in A, okay, A has 2, B has 2, okay? A has 4, B has 4, 6, 6, okay? So everything here can be found here. So in that case, we'll say that B is a subset of A. Although in this case, A is not necessarily a subset of B because only B is a subset of A, the reverse is not the same, okay? But when we have to reverse this for any reason, we say that A is a superset of B. A is a superset of B. Okay, right. Now, there is something very important you must take note here. So I'm going to be teaching this and this at the same time. When we did video, is it in video 1 or video 2? Lesson 1 or 2, I think it's lesson 2. When we were, just discussing certain things about sets, like the symbols used in set theory, I told you that this symbol means proper subsets, right? But it's not really so. It's actually the other way around. That is a misplace of property, okay? And I beg your pardon on that, please. So I just really want to correct something. It's just the other way around. Now, this is how it goes. You see, this equality symbol that you're seeing under it is not there for design. It is there telling you something. It is actually passing a message. And the message is that we all know, or it is a general rule in mathematics or in set theory, that every element is a subset of itself. I will prove it to you. If a set C is equal to 1, 2, 3, if set C is equal to 1, 2, 3, all right? So you see that if I have a set D that is equal to 2, 3, 1, okay? And I have a set E equal to 1, 3, 2. Okay, based on what we learned in about equal sets, we all agree that C is equal to D. We agree also that D is equal to E. We also agree that C is equal to E. All right, okay, and then we agree about these three, right? That set C is equal to set D, or set D is equal to E, or C equal to E. All right, or simply we agree that C is equal to D and equal to E. Okay, they're all equal to each other, right? Good. Now look at this. Then if C is equal to D, then it means that, and then if we also agree that D is a subset of C, right? We also agree that, if you can agree with me, that D is a subset of C, which means all the elements of D can be found inside C, which is also very true, right? And then, so we see that D is a subset of C, and D is also equal to C. So in that kind of situation, then we can say that D is a subset of C. Reason being that D is a subset of C, and also D is equal to C. Do you understand? It carries that equality property. And that is the reason why we have this thing under it. It's just like the common sense understanding of the reason why something like this is there. So, therefore, this does not represent a proper subset. It only represents a subset. Please, I beg your pardon. I'm going to correct, I'm trying to correct that little error that I made in video 2. Okay, it's like omission. When I was watching the video, I figured out that I made that mistake, so I decided to use this particular video to correct it. Okay, so please. Now, this equality symbol under this simply means that it is a subset, but not a proper subset. Okay? Now, the difference between subset and proper subset, I explained in that video that a subset is a proper subset of another. A set is a proper subset of another set if two conditions are met. Condition number 1, all the elements in the set can be found in the other set. Condition number 2, this set is not equal to that. Okay, so which means if I want to apply the condition for proper subsets, okay, let me say set A is equal to 1, 2, 3, maybe up to 10, and then set B is 1, 2, 3, 4, 5. Let me just put it this way. All right, in this case, B is a subset of A. Reason being that every element in B can be found in A. So that is why B is a subset of A. And also, B is a proper subset of A. You know why? The two conditions for proper subsets to be in place, for you to call is a set, for you to say that a set is a proper subset of another set, for you to say that B is a proper subset of A, for that condition to be, for you to mention that, two conditions. Condition number one is that all the elements of B can be found in A. That is the first condition. All the elements of B can be found in A. First condition. Condition number two is that for B to be a proper subset of A, then it means that A or B, any one of them anyway, B is not equal to A. So if these two conditions are met, then it means that B is a proper subset of A. So which means why general subset is represented by this, proper subset is represented by this. Okay? All right. Not the other way around, the way I mentioned it in that lesson 2, which was an error. Okay? Please pardon me for that. Okay, but then the thing is just that this is used to represent just normal subsets. Why this one is used to represent proper subsets. Okay, all right, so that is the difference between the two. Okay, now, why does the word proper come in? The word proper comes in because of the fact that every set is a subset of itself. So we have to differentiate. We have to be able to distinguish a subset, a set that is not a subset of itself, or not exactly the same number of elements. So which means that if C is equal to 1, 2, and 3, okay, and D is equal to 3, 2, and 1, it means that D is a subset of C, okay, because of the fact that everything found here, it can be found here. And C is also a subset of D, because everything found here can be found here. So at the end of the day, okay, the two of them could be struggling for which one comes first. I'm just like trying to make it analogical, okay? So, but in this case, there is no struggle. Clearly, B is a subset of A, but the other way around is not true, which means A is not a subset of B. So no arguments, everybody knows his place. In that situation where everybody knows their place and there is no argument, okay? So there is no form of ambiguity. In that kind of case, we say it is a proper subset. But when there is ambiguity, like something, you can say that A is equal to, like C is equal to D, and you can also say D is equal to C, and then, you know, and all of that, then that's not, they are subset to each other, but not proper subsets, okay? So, but then, just for the sake of representation, and we generally just use only this one, be it proper subset or ordinary subset. For calculation, for everything, you know, for the sake of anything, we just stick to this one. Do you understand? So that is it. So for the rest of this course, we are going to stick to this, but just be aware that there is something like a proper subset and ordinary subset. Ordinary subsets are just represented this way, proper subsets represented this way. But for the sake of the remaining part of the material, whether it is ordinary or proper, we just stick to this form of representation for general purpose. All right. So this video is getting too long. In the next video, I'm going to explain the last 5. Okay. So that is that as for that. And don't forget this. Always remember these 4 key things. You learn, you understand what you learn, try to apply the knowledge by practicing, and then you excel. Very certainly. See you in the next video. Bye.